Welcome back to The Explainer. Today, we're diving into the unsung heroes of our modern world. I'm talking about a super simple family of molecules that, believe it or not, powers our cars, heats our homes, and even makes up the wax in our candles. Let's get right into it.
So let me ask you something. What did the propane in your BBQ, the gasoline in your car, and just a regular block of candle wax all have in common? I mean, really think about it. One's a gas, one's a liquid, and one's a solid. They seem totally different, right? Well, it turns out, chemically, they're all part of the very same family.
And that family is the alkanes. At their very core, they are just about as simple as it gets in organic chemistry. All you have is a chain of carbon atoms, and then every single open spot is filled up with a hydrogen atom. And everything is held together by these really strong, really stable single bonds. They're basically the fundamental backbone of so many things we use. Okay, so to really get a handle on these guys, let's get to know the family a bit better. We can start with their nickname, which actually tells you a whole lot about their personality.
You'll often hear alkanes called paraffins. Now, that name comes from the Latin param affinis, which literally means little affinity. And that is a huge clue to how they behave. They have very little affinity for reacting. They kind of like to keep to themselves and don't really mess with acids, bases, or most other chemicals, at least not under normal conditions.
All right, so we know they're not very reactive with other chemicals, but what about with each other? How do they interact among themselves? Well, that all comes down to their physical properties, and we can start with an example you already know really well. You know how oil and water just do not mix? That's all about something called polarity. See, water is polar. It has a slightly positive end and a slightly negative end, almost like a teeny tiny magnet. Alkanes, though, are the complete opposite. They're nonpolar. Their electrical charge has spread out perfectly evenly, and the rule in chemistry is like dissolves like. So polar and nonpolar things, they just don't mix. It also explains why alkanes are fantastic for dissolving other nonpolar stuff, like grease. And here's something that's just wild. The size of an alkane molecule completely dictates whether it's a gas, a liquid, or a solid. The really tiny ones with just 1 to 4 carbons, they're gases, like methane. Once you get a longer carbon chain, say from 5 to 17 carbons long, they become liquids, like the stuff in gasoline. And then, if you have 18 carbons or more, they pack together so tightly they become waxy solids, just like a candle.
So why does size matter so much? It's all because of these weak little forces between molecules called van der Waals forces. The best way to think about them is like a kind of molecular static cling. For small molecules, that cling is really weak. But as the molecules get bigger and longer, they have more surface area, and that clinginess really starts to add up. It gets strong enough to hold them together, first as a liquid, and then eventually as a solid.
But wait, it's not just about the size. The shape is also absolutely critical. Just look at these two molecules here. They have the exact same number of carbons and hydrogens. They're isomers. But check out their boiling points. They're completely different. The long, straight one needs a much higher temperature to boil than the one that's all balled up. And the reason for that is just simple geometry. A long, straight molecule has all the surface area to cling to its neighbors. But when you add branches, the molecule becomes more compact, more like a little sphere. It just can't get as close to the other molecules, which means less surface area for those van der Waals forces to grab onto. It's kind of like trying to stack a bunch of bowling balls versus stacking planks of wood. The planks stick together way better. Okay, so we've got a handle on their physical nature. Now let's switch gears and look at how they behave chemically. We already know they have that little affinity for reacting, but they do have a couple of really important reactions, especially if you give them a little push with some energy. The most famous reaction, the one we rely on every single day, is of course combustion, burning. Alkanes are incredible fuels because when you burn them, they break apart and release a massive amount of energy as heat. And how much energy are we talking about? Well, let's take methane, the simplest alkane of all. If you burn just 1 mole of it, which is only about 16 grams, it releases a whopping 890 kilojoules of energy. That's a huge amount of power from such a tiny molecule, and it's what's heating our homes and cooking our food. Now, what gets made when they burn is super important. If you have plenty of oxygen, you get what's called complete combustion. The only products are harmless carbon dioxide and water. But if there isn't enough oxygen, you get incomplete combustion. And this is bad news because it creates carbon monoxide, CO, a gas that's colorless, odorless, and extremely poisonous. So even though alkanes are pretty unreactive, you can kind of force them into it. Halogenation is a perfect example. You take an alkane and a halogen, like chlorine gas, and you blast it with UV light or a lot of heat. That energy is enough to split the halogen molecule into these super reactive things called free radicals. These radicals then go on the attack, ripping a hydrogen atom off the alkane and taking its place. It's a classic substitution reaction. There's another really cool way to use energy to change alkanes. It's a process called pyrolysis, but everyone just calls it cracking. You take really big, long alkane molecules and you heat them to super high temperatures, but without any oxygen around. This literally cracks them apart into smaller and often much more valuable pieces. For example, a single hexane molecule can break apart into a few different combinations of smaller, more useful molecules. So let's connect all of this, their physical properties, their chemical reactions, to the huge impact they have on our world. Because these little chemical tricks are basically the foundation of the entire petrochemical industry. A process called reforming takes things even one step further. In this case, chemists take those straight-chain alkanes, and by using special catalysts, a lot of heat, and high pressure, they can actually get them to lose some hydrogen atoms and curl up into stable ring structures, like benzene. This is a crucial step in making high-quality, high-octane gasoline. So let's just put it all together. Their ability to burn, combustion, makes them amazing fuels. The process of cracking lets us take heavy, less useful oil and break it down into valuable stuff. In reforming, lets us build even better fuel molecules. Every single property we've talked about is being used on a massive industrial scale every single day. And that really leaves us with a final big thought. There's just no denying how useful alkanes are. They are the absolute bedrock of our energy and chemical industries. But we also know that burning them contributes to greenhouse gases and climate change. So the huge question we all face is, how do we balance their incredible utility with their environmental footprint? That's the challenge for all of us, right now and into the future.